Hey there! Let's see how you can create a smart contract application on Hedera using Solidity, React.js, MetaMask, and EthersJS. We're going to focus on a simple counter, and the goal is just to understand the fundamentals of building a dApp so you can create more complex ones in the future. If you want a written guide of everything we're about to do, make sure you check out this article in the Hedera blog site. The article covers all the requirements and all the steps in detail, and it points you to the GitHub repo, which is also linked in the description of this video. Let's take a look at the architecture of our application at a high level. This diagram shows all the different components and the interactions between those various components in our dApp. You see the browser, which is where you will interact with the dApp. You also see a signer, in this case it's MetaMask. Now, a signer is a crucial component in Web3 applications because it is what facilitates signing transactions and messages using the private keys while those keys remain safe in your wallet. Next, you see the front end of the application, which is built using React. You see a JSON RPC provider, which has an API for sending transactions and querying data from the network. And then we have the Hedera network, which has consensus nodes that process and validate transactions, and mirror nodes that store transaction data. Now, the Hedera network has 3 services, and at the moment, the JSON RPC interface only exposes the 2 that you see on the diagram. Now that we saw the architecture and connections between components, we can more easily understand the flow of interactions and data in our counter application. The first thing to do is to clone the GitHub repo with the example code so you have a starting point. You have 2 options. If you want to quickly run this from the browser, then you can try this example using Gitpod. So you can get the link from the tutorial or from the video description below. Setup looks something like this once it's ready to go. If you want to clone the repo locally, then you can just follow the steps in the tutorial to clone, install all the dependencies, and start the application. Once your development environment is good to go, it's time to get familiar with the structure of the code and the UI of the application. You see, it is a simple UI with 3 buttons. So the first button connects the application to MetaMask, the second button deploys the counter smart contract, and the third button executes a contract function to increase the count. Now let's look at the app.jsx file behind this UI. You can think of this code as 3 main sections, in addition to the imports. You have the state management part, which uses the useState hook. You have the functions that are executed with each button press, and we're going to look at these in a few seconds. And then you have the return statement that groups the elements that we see on the page. If we take a look at our React components, you see that my group is a functional component that combines both a text and a button element and receives props as arguments. In this case, it receives a function to execute, a button label, text, and a link. So we're grouping components and customizing them to be able to reuse them. That's one of React's advantages, which results in a more composable, well-organized, and easy-to-read application. Looking at the code for my group, there you see the elements being grouped and the properties being passed accordingly. If we look at my button, there you see that it's just a button element where we specify the functions to execute on click, some class styling, and the button label. And if we look at my text, there you see that if there is a URL being passed in the props, we link to that URL, apply some class styling, and display the actual text. If there's no URL, then we just display the text with the right styling. So just to reiterate, the point of this section is that we're working with these components that are reusable so that we can just take them and make them behave differently in other parts of the application. So now that we know all that, let's jump into the function connect wallet, which is the function that will execute when we click on the first button. You see that here we're taking care of a few things related to the front end so that we don't have to spend this whole video on React coding. For instance, if an account is already connected, then we display that. Otherwise, if there is no account connected, then we call the wallet connect function. So this is the key part that we will code in this section. So if we go to this wallet connect function file, you see that this file starts by importing EthersJS, and also by defining the network that we will connect to, that is the Hedera network. The first step here in the function is going to be to initialize an Ethers provider. This Ethers provider comes from EthersJS, right, which connects to MetaMask, which is our signer. And this Ether provider is like a bridge between the application and the Hedera test network because it enables you to send transactions, query data, and also interact with the smart contracts. The next step in the function is to determine the chain ID based on the Hedera network that we chose. In this case, it was the testnet, but we could also do preview net or mainnet. So here we see the chain IDs for each one of the Hedera networks. So for testnet, it's 0128 in hexadecimal, 129 for preview net, and 127 in hex for mainnet. Then the next step in the function is to send a wallet add Ethereum chain request to MetaMask so that we can add the appropriate Hedera network. And this step is very important because here is where we do things like setting the native currency, which is HBAR. And we also provide the RPC URLs and also the URLs for the network explorer that we're going to use. For JSON RPC provider, we're going to use Hash.io, which is a JSON RPC relay community service provided by Swirls Labs. Now, remember that anyone can host their own relay, and they can also use a commercial provider like Archaea. Now, for Network Explorer URL, we're going to use Hashscan, which supports EIP 3091, so it makes it really easy to see transaction information in wallets like MetaMask. And the last thing we'll do in this function is send an ETH request account to MetaMask so that we can access the Hedera account of the user. And once that connection is successful, then we'll return the account that was selected. And of course, we return a few bits of information like the selected account, provider information, and also the network that we're connecting to. After that, we return to our app.jsx file. We come back to our connect wallet. And here we update the React state with the information on testnet account, the network, and other wallet data so that we can display the connected testnet account and interact with the smart contract that we're going to deploy in the next step. So if we test our application now with the code that we have added so far, we click on Connect Wallet. There we see first the request to change networks, and then we see the account selection part. Now in this case, I have already added a Hedera testnet account. In this case, it is my testnet account from the Hedera developer portal. So that is the account that I'll select and confirm. And then we see the updated text in our front end confirming the connection and displaying the account information that was selected. And when we click on the hyperlink in the text, we see the account information from the network explorer that we've been using, which is Hashcan in this case. All right, now let's see what happens when we click on the second button to deploy the smart contract. Just like before, contract deploy is the function that will execute, and it will start by taking care of a few front-end things, like making sure that a wallet is connected first. Then this function will call contract deploy function, or contract deploy FCN, while passing the wallet data that we obtained in the previous step as the argument. And you see that this function will return the contract address that is deployed. So this is the part that we will code next. But before we do that, let's take a quick look at our Solidity contract. So this counter contract has a state variable called count, and it also has an increment function that increases the count and also emits an event when that function is called. Now, if you're not too familiar with events in Solidity, these just provide a way to log things and actions that take place in your smart contracts. And so when an event is emitted, it stores the arguments in a data structure that is called the transaction log. Now, you can learn more about working with events in this other tutorial that we have. Now, coming back to our deploy contract FCN, the first action is to extract the Ethers provider and the signer from wallet data. Then we specify a gas limit when it's time to deploy the smart contract. And we also initialize a contract factory object from Ethers with the API, the bytecode, and also the signer that deploys the contract using the gas limit that we specified. Now, in Ethers, a contract factory is an object that helps you deploy a new smart contract, whereas the contract class is typically used to interact with contracts that have already been deployed. So there you see that we wait for a confirmation for the transaction, and once the deployment transaction is confirmed, then we extract the contract address. And then we also return that to our contract deploy function that is in app.jsx. So coming back to our contract deploy function, here is the contract address that is returned. And just like before, we update the React state with the contract address and some text and link information for our front end. Now, if we test our application with the code that we just added, we can click on the Deploy Contract button. There you see the confirmation dialog for the transaction on MetaMask. We confirm, and once the contract deploys, we'll be able to see the updates in our front end. So there is the address of the contract that was deployed, and if we click on that hyperlink, then we can see the information in Hashscan about the contract that we just deployed. So here we have the contract ID, EVM address, and additional information about the contract entity. And so now our final step is to interact with the contract that we just deployed. So for that, it's time to take a look at the contract execute function that is in the app.jsx file. So this contract execute function handles a few UI tasks, for instance, making sure that a contract is deployed first, and then it also calls the contract execute function or contract execute FCN once that third button is pressed. Now, notice that here we're passing the wallet data and also the contract address as input arguments, and then we're capturing the transaction hash and also the final value of that state variable count as the outputs of this function. So if we now go to this contract execute FCN, there you see we start with the imports like the API. We're importing Axios to be able to query the mirror node REST API. We're importing EthersJS to be able to interact with our contract. And we're introducing a delay that we will use when it's time to query the mirror nodes. So here is contract execute FCN. Here are the inputs that we're passing. And the first step is going to be to define the provider and the signer. Again, we do that by extracting that information from wallet data. Then when it's time to execute the smart contract function, the first thing that we will try is to check the state of the smart contract, right? We want to check what the initial count is. For that, we're going to use this function called getCountState. We can see that down here. And the way this function works is by using Axios to get the state of our smart contract using the mirror node REST API. So you can get more information about how to use this REST API in our documentation. We also have tutorials for this. And then once that count information is obtained, then we do a little bit of logic here to convert that value from hexadecimal to integer. And of course, if it is the first time that we're getting this value, then that decimal value should be 0. Then this function returns the count in decimal, and that is actually what you see as initial count over here. So we output that to the console. Then it's time to actually execute the contract function. We do that with the contract object from Ethers. We also use the contract address, the ABI, and the signer. There we use the function that we want to call in the contract. We wait for a confirmation, and once we receive a confirmation, we extract the transaction hash for our contract interaction. Then the last thing that we want to do is check the smart contract state once more, right? So we start by introducing a delay of 5 seconds just to allow for the mirror nodes to update before performing this query, since they have to get the information from the consensus nodes. Then we call the getCountState function once more to get that final count value. And we output some information to the console for debugging. And finally, we return the transaction hash and the final count as we saw in app.jsx. So coming back to our contract execute function in app.jsx, here we see those outputs. And we perform some additional tasks related to the UI so that we can actually get the latest text and latest link information about our transaction hash and the final count. So once we test the application with the code that we just added, for the third button, we can click on Execute Contract. There we see the transaction confirmation dialog in MetaMask. And once we confirm, after a few seconds, we should see the updates in our front end. So now if we click on this link, that takes us to the transaction confirmation in Hashscan, where we can see information about the results, the actions that take place in the call trace, additional information about the state. For instance, we see the count value here being written to the state of the contract, and additional information about events being emitted in the log section of this transaction. So that is all. That is a lot of ground. And as a recap in this tutorial, we started from the GitHub repo. We then did an overview of the dApp structure and the UI. Then we connected our dApp to our Hedera account in MetaMask. Right, in this step, we actually selected the Hedera testnet. We then deployed a counter smart contract using EthersJS. And finally, we interacted with that contract to increase the count, and we saw the relevant information in the Network Explorer. So be sure to check out the written guide of this tutorial and continue learning in our documentation. Thanks for watching, and I'll see you next time.